Lecture 3, Leader Election in the Rings. Preface, recap of previous lecture. In previous lecture we have discussed the formal model of distributed message passing system, that is synchronous and asynchronous timing models with no failures. We have seen in the previous lecture a few simple algorithms for message passing systems, and these algorithms were to understand the concepts and the complexity measures in the distributed algorithm design. The algorithms which we have seen in the previous lecture used to solve the problem of broadcast, converged cast, DFS, and is being used as the basic building block for the distributed algorithms. Content of this lecture. In this lecture we will discuss the leader election problem in a message passing system for a ring topology, in which the group of processors must choose one among them to be a leader. We will present the different algorithms for leader election problems by taking cases like anonymous or non-anonymous rings, uniform or non-uniform rings, and synchronous and asynchronous rings. So let us begin this particular introduction of leader election problems. So in this particular lecture we are considering the topology of a message passing system as a ring. So ring is a convenient topology and is basically resembles to the physical token ring and corresponds to the ring structure of a physical ring and is easy to understand or design the algorithms in this particular setting, that is basically the ring structure. So the leader election problem has several variants. Leader election problem is for each processor to decide that either it is a leader or a non-leader, subject to the constraint that exactly one processor decides to be a leader. So leader election problem represents a general class of symmetry breaking problems. So for example, when a deadlock is created because of the processors waiting in a cycle for each other, this particular deadlock can be broken by electing one of the waiting processors as the leader and removing it from the cycle and thus breaking the deadlock. So this is called, this particular example is a example where the symmetry breaking is applied in the form of a leader election algorithm. So leader election definition, the processor, each processor has a set of elected, that is one, and non-elected states. So once a elected state is entered, the processor is always in an elected state, and basically similarly for the non-elected states. So in every admissible execution, every processor eventually enters an elected or a non-elected state, and exactly one processor, that is the leader, enters an elected state. So again, the use of leader election algorithm, we are going to stress upon this use to motivate the basically construction of the leader election algorithm. So leader election can be used to coordinate activities in a distributed system. So for example, finding a spanning tree using the leader as the root. So we have seen that it becomes easy to basically construct a spanning tree, that is DFS, if the root is given, and to identify the root in a network, leader election algorithm can be used. Similarly, if in a token ring network, if a token is lost, then to reconstruct the lost token, a leader election algorithm can be of great help. So leader election algorithm will identify one of the node, and that particular node will recreate the token and will resume the token ring structure. So in this lecture we will study the leader election in the message passing system, that is called the ring structure. So we are going to now describe about the ring topology. So in an oriented ring, processors have a consistent notion of left and right. So, for example, this particular diagram which is illustrated over here, you can see the processors P0, P1, P2, P3 and P4. They have P0 and P1, they have the channel. So, P0 is connected to P1, on the left side it is numbered as 1, and P1 is connected to P0 with a number that is 2, that is called the right side. So, if we see all the numbers as 1, then the orientation of the ring is basically nothing but the orientation of a ring is a clockwise. So, if we basically keep on navigating over the number 1. Similarly, if we are navigating over number 2, that is P0 is basically communicating with P4 and P4 is P3, that is through the number 2, then basically it is a counterclockwise. So, this is called oriented ring. So, orientation of a ring can be basically formed using these numbering of a channel, and that is to be done by the processors at its own level, that is a local level with a local knowledge. So, for example, if the messages are always forwarded on a channel 1, they will be cycled clockwise around the ring. So, why we study the ring? Because in a message passing system which is basically used as a ring structure or a ring topology, gives a starting point and also easy to analyze the algorithm and design the algorithm in this particular setting that we are going to see, that is a leader election algorithm. This abstraction of this particular ring is a token ring also. So, and the lower bounds and impossibility results for the ring topology also applies to an arbitrary topologies. So, whatever algorithms we are designing in this particular setting can also be applied as well in arbitrary topologies. So, the different kinds of rings we are now going to start and discuss. The first type is called anonymous rings. In anonymous rings, the processors do not have the unique identifiers. That means all the processors are anonymous, and thus the ring formed out of these processors without having any IDs, unique IDs, they are called anonymous rings. So, in this particular setting, each processor will have the same state machine, and also the algorithm relies on knowing the ring size, that is how many number of processors are there. Then there is another kind of ring structure, and that is called basically a uniform ring. So, uniform ring will have n nodes, but this particular number of nodes are not known, then it is called uniform, because all the processors are now uniform. The algorithm which uses this information, that is without knowing the ring size, called uniform algorithm. So, uniform algorithm does not use the ring size. Formally, every processor in every size ring is modeled with the same state machine here, and that is why it is called uniform algorithm or uniform ring structure. A non-uniform algorithm uses the sizes of ring in the algorithm design. So, formally, each value of n, every processor in the ring of size n is modeled with the same state machine, that is of an. So, that means for a different ring size of value n, different algorithms or different state machine will represent by an. Now, we are going to see if the ring is anonymous, that is the unique IDs are not given to the processors. So, about in this particular setting, about the structure, that is a ring leader election algorithm, how it will work in this particular setting. So, there is a theorem which says that there is no leader election algorithm for anonymous rings, even if the algorithm knows the ring size, that is if it is non-uniform, and also it is basically following a synchronous model. So, this result is called impossibility result. That means no leader election is possible if the ring is anonymous, that is if the IDs are not given. We are going to see the proof, and then this impossibility results will be used in as basically a information to develop the leader election algorithm. So the proof sketch goes like this: every processor now begins in the same state with the same outgoing message, since they are anonymous. So every processor receives the same message, does the same state transition, and sends the same message in the round 1. Now you may ask, if a processor is sending the message, to whom it is sending, how it will know to whom it is going to send, or who is the destination. Then you have seen that the channel numbers, that is, if it is oriented ring, that means if it is a clockwise, then it will always basically send to the channel 1, and so on. So basically the channel numbers will be used instead of if the IDs are not known, and this particular structure will represent the same state machine. So same message will be transmitted and same state transition will happen after the receipt of a message. So eventually some processor is supposed to enter in an elected state, but then all would enter into a elected state. So in this particular setting, if we analyze using the safety property that never elects more than one leader, here every node is elected as a leader, or liveness eventually elect at least one leader is also violated. So if so in this particular proof, we have seen that there is no leader election algorithm for anonymous rings. Now since we have proved this theorem for since the theorem was proved for non-uniform and synchronous rings, and the same result will hold for a weaker models. Weaker models in the sense, if it is uniform means the value of n is not known, and also a weaker one, that is called asynchronous timing model, then also this particular theorem holds and leader election is not possible for anonymous rings. Now we are going to discuss the rings with IDs, because if the leader election is not possible in basically the anonymous rings, then we are going to consider the ring structure with the unique IDs. So IDs are assigned out of the natural numbers, and so each processor has a unique ID now. So now we are going to discuss about that IDs, how the IDs are assigned. So specifying a non-anonymous ring where each processor is assigned a unique ID is illustrated in this particular diagram, and I will be explaining you through this particular example. So start with the smallest ID from here. Smallest ID is 3. So let us note down this particular ring in this manner and list IDs in a clockwise order. So clockwise order goes like this. So first ID is 3, then the next ID is 37, and furthermore the next ID is 19, then 4, and finally 25. So just see that this particular structure, if this rule is followed, then it will give a oriented ring. And this will be a non-anonymous oriented ring structure, which we have seen as an example, and this particular structure will be used to design the leader election algorithm. So non-anonymous algorithm, if it is uniform, that means there is one state machine for every IDs, and no matter what the size of the ring. That means the algorithm in this particular setting does not know the size of the ring, that is n is not known. Non-anonymous, it knows the value of n. There is one state machine for every ID and every different ring size, and basically it will form a non-uniform, non-anonymous algorithm. So these definitions are tailored for leader election in the ring. So now we are going to discuss the first leader election algorithm with the message complexity of the order n square, and this algorithm is called Leland Chang robot algorithm, that is LCR algorithm. So it's the simplest algorithm, and it will give the start point to understand the leader election algorithm design in a distributed system. So here every node, every processor will send the value of its ID to the left in a form of a message. So we can see this particular example. So every processor will have the IDs, and that is unique ID because it's a non-anonymous ring. Now send the value of its ID. So it will send a message with its ID 0 to the left. Similarly, this also will send, and everyone will send its values. Now when an ID j here from the right it will receive the message, and if the j, that is the ID of incoming message, is greater than its ID of a receiving process, then it will forward to the left. Here in this case, this situation is not considered, this situation is not happening. The second j is equal to ID, that is also not satisfying, and if j is less than ID here, then it will do nothing. That means 0 will not be, this particular message will be swallowed, and this particular structure will go on. So you see that in this structure here, this will also be swallowed, this message will be swallowed, this message will be swallowed, but this will continue, and this again will be continued over here. So 2 message of size 2 will continue over here again, and this will also forward it. So 2 will come again over here from where it is being originated. So the correctness of the algorithm goes like this, that it will always elect a processor with the largest ID, and the message containing largest ID passes through every processor and basically comes over here again. As I told you, the message of a processor ID with the highest ID will goes along the entire ring and comes back to it, and it will be elected as a leader. And all other nodes, then after electing a leader, it will send a message that is called a termination message, and all other nodes will become a non-leader. So the time which is taking here in this algorithm is of the order n, and the message complexity, if we analyze, it depends on how the IDs are arranged. So the largest ID travels all around the ring, that is, it will basically result into n different propagation of the messages. Second largest ID will travel until reaching the largest one. Third largest ID will travel until reaching the largest or a second largest, and so on. So we can understand using this particular example the message complexity, that is order n square. So just see that here the ID which is the highest ID, that is the ID which is number 4, will be propagated along all the ring and will come back over here again. Similarly, the second lowest ID, that is 3, will propagate, and it will not pass through P4. Why? Because it is having the highest ID, it will swallow this particular message. So this particular messages are being flowing. So if we count how many messages are, total number of messages is being flown, you can see that the highest ID will basically result into n different messages. Next largest ID will have n minus 1, n minus 2, and so on up to n. So if we sum up, it will become the n square. So this particular topology will incur into n square number of messages. So that is why the message complexity of this algorithm is of the order n square. So big O of n square. That means this particular topology this example of a topology we have seen where exactly n square messages are required. Maybe in other topologies it will require even less than n square, but in no situation the number of messages will exceed n square, and that is why this particular algorithm guarantees that it will take n square number of messages. So again, this particular analysis we can see from this particular diagram that in any admissible execution it will send never more than order n square messages, that is written over here. Moreover, there is an admissible execution in which the algorithm sends theta n square messages, that we have seen in the previous example. Here also in this example you can see, consider a ring where the identifiers of the processors are 0, 1, 2 and so on. They are being numbered and they are ordered in this particular figure. So in this configuration the messages of the processor with identifier I is sent exactly I plus 1 times, and the total number of messages including the n termination message is n plus n is the total number of termination message, and this is the total number of messages which is sent by the other processor to elect a leader. And in this particular ring you can see this particular structure, that a processor that is an ID n minus 1 will basically navigate for n different messages, will propagate n different messages. So a particular processor I will basically propagate total number of exactly identifier is propagated I plus 1 times. So if we sum up this particular formula, again it will give theta n square, and this theta n square, that means in this particular topology it will basically incur n square messages. So this particular algorithm never incurs more than n square in any admissible execution. Now the question is, can we develop an algorithm which will use fewer than these number of messages, that is order n square message? So that is an idea, and we are going to see another algorithm. So the next algorithm will be based on this idea, is that why so many messages are used, can we reduce the number of messages? So here it is, the idea is saying that try to have messages containing a smaller ID travel smaller distances in the ring. So that means smaller IDs are not going to elect as a leader, so why they are traveling more distances, they can be contained in a smaller region, and only the IDs with a higher IDs or larger IDs are allowed to travel across all the ring. So this way we can curtail number of messages in this particular algorithm. And with this idea and another algorithm we are going to see, that is called big O of n log n messages, that is leader election algorithm, is given by Hirschberg and Sinclair. HS algorithm, it is well known algorithm. So we are now going to describe this algorithm in more details. So to describe this algorithm, we first define the k neighborhood of the processor Pi in a ring to be the set of processors that are at a distance at most k from Pi in the ring, that is either to the left or to the right. Note that the k neighborhood of a process includes exactly 2k plus 1 processor. To understand this through a diagram, so you can see a ring of 3 nodes. In this particular node, the k neighborhood of this particular processor Pi, one neighborhood of this processor is nothing but the left and the right. Only 2 processors will be there. Similarly, if this particular, instead of 1, if it is k neighborhood, so many k number of processors will be on the left, k number of processors on the right. So this means that a k neighborhood of a processor includes 2k plus 1. So here one neighborhood will include 3 processors. So this algorithm, that is big O of n log n messages leader election algorithm, will require the knowledge of k neighborhood of a particular processor Pi for all the processors. So the algorithm operates in the phases. So it is convenient to start numbering the phases with 0. So in kth phases, so 0th phase we have seen. So in kth phase it is convenient to start the numbering with the phase 0, and kth phase a processor tries to become a winner of that phase. To be the winner, it must have the largest ID in its 2k neighborhood. Only the processors that are winner in the kth phase continue to compete in the k plus 1th phase. Thus, fewer processors accede to a higher phase until at the end only one processor is the winner and is elected as the leader of the whole ring. So let us see more detail about phase 0, and then we will see about phase k. So in phase 0, in more detail, phase 0, each processor attempt to become a phase 0 winner. Take the same example. So in phase 0, every processor will initiate and try to become a phase 0 winner. Let us have these IDs 0, 1 and 2. So to become, each processor attempts to become a phase 0 winner and sends a probe message containing its ID to its one hop neighborhood, that is to each of its two neighbors, left and right. If the identifier of the neighbor receiving the probe is greater than the ID in the probe, it swallows the probe, otherwise it sends back the reply message. So here in this case it is 1 and it is 2. So the ID of the processor receiving the probe message with the ID 0 has having higher ID, it will swallow it. Similarly here also it will swallow, it will not give back the reply. But here in this case, if node 2 sends the probe message, both the message will send back the reply. Sends back the reply. If the processor receives the reply from both its neighbors, then the processor becomes a phase 0 winner. So here processor 2 becomes phase 0 winner because it has received the replies from both of its neighbors and will continue to a phase 1. So we are going to describe about if a processor is winner in a phase k minus 1 and now it is eligible to be participating in phase k. So phase k, that is in general, in phase k a processor Pi, that is the phase k minus 1 winner, sends the probe message with its IDs 2 raised power k neighborhood, that is one in each direction. Each such message traverses 2 raised power k processors one by one. A probe is swallowed by a processor if it contains an ID that is smaller than its own ID, that we have also seen in the phase k. If a probe arrives at the last processor on the neighborhood without being swallowed, then that last processor sends back a reply message to Pi. If Pi receives a reply from both the direction, it becomes a phase k winner and it continues to the phase k plus 1. So the processor that receives its own probe message terminates the algorithm as a leader and sends the termination message around the ring. So if we can see, if this is the ring, so every node will have 2 raised power k neighborhood. For a phase k, so 2 raised power k neighborhood on the left, 2 raised power k neighbors on the right. If that particular message goes through the last node in each of these 2 power k neighborhood on the left and right, if it is basically going through up to the last one, then it will send back the replies and it will the winner of k phase of the algorithm. It will be eligible to proceed to the k plus 1th phase. So that I have explained you the phase k of this particular algorithm. The entire algorithm is explained over here. So here you can see that the probe structure will have three different information. The first information is called ID, the ID of the node which has initiated on a particular phase and in which phase it is initiating. So that phase number is given, and the hop count because it has to traverse through 2 raised power k neighborhood. So here it is, let us say 2 raised power k hops, how many hops, and this is the phase number, which phase message it belongs to, and the IDs which particular. So in this particular send message, you can see that the probe has 1, 2, 3 different arguments. 3 arguments means ID of that particular processor which has initiated that particular leader election in phase 0, and it is going to send to one hop neighborhood to the left and right that we have seen. Now upon receiving this particular probe with J, K and D, J means the ID of the probe message, K means the kth phase, and D means the number of hops it has traversed so far. So upon receiving this probe from the left, and it will also receive from the right, it will perform 3 different cases. Now if J is equal to ID, that means the message which has traversed along all the nodes or processors of the ring and came back to the same point, then that node will be terminated and elected as the leader. Now if J, that is the receiving message, his ID or his ID is greater than the node which is receiving this particular message, and also if the number of hops is less than 2 raised power k, then it will send the probe to the left and to the right as well, depending upon from where the message it is being received. Now if the number of hops is reached to 2 raised power k on the left side or on the right side, then it will send the replies message. So it will send the reply in that case because it has reached 2 power k hop neighbors, then it will send the reply message. So it has to decide based on whether it has reached 2 power k, the last node of 2 power k neighborhood. If it has, then basically it will send the reply, otherwise it will keep on forwarding the probe. So all 3 cases are given. Now upon receiving the reply from the left and the right, if J is not equal to ID, then it will send the reply to the right, that means it will keep on forwarding the replies if it is not equal to ID, and if it is ID, then the reply will be reached. If already received reply from J from the right and from the left, then it will be the winner of phase k, and it will start the probe for k plus 1th. So the structure will be the same node which is the winner of kth phase will go and send the probe at k plus 1th phase or initiate the k plus 1th phase, and basically the number of hops it will basically begin, and this hop count is initialized to or is being sent to 1 and keeps on incrementing till it will reaches 2 raised power k, and there these 2 conditions are being checked, whether the probe is to be moved forwarded or it is to be returned back to the originator. So this algorithm is explained, which is called a big O of n log n leader election algorithm in a ring. So the pseudocode which appears in the algorithm 5, we have just seen that algorithm 5. The phase k for a processor corresponds to the period between its sending of a probe message in line 4 or a line 15 that I have explained with the third parameter k, and it's sending of a probe message in line 4 or 15 with the third parameter k plus 1. The details of sending the termination message around the ring have been left out in the code, and only the leader terminates. The correctness of the algorithm follows in the same manner as in the simple algorithm, that is over n square algorithm, because they have the same solving rules. It is clear that the probes of the processor with the maximal IDs are never swallowed. Therefore, this processor will terminate the algorithm as the leader. On the other hand, it is also clear that no other probe can traverse the whole ring without being swallowed. Therefore, the processor with the maximal identifier is the only leader elected by this particular algorithm. So again, more description about this algorithm. So each processor now here in this algorithm tries to probe successfully larger neighborhoods in both the directions. That is, the size of the neighborhood doubles in each phase. Now if the probe reaches the node with the largest ID, the probe stops. If the probe reaches end of the neighborhood, then the reply is sent back to the initiator that I have explained you in the algorithm. If the initiator gets back the replies from both directions, then it goes to the next phase. That also is explained in the algorithm. If the processor receives a probe with its own ID, then it will elect itself a leader. The same thing is explained here in this particular picture. So this is, now you can very easily identify this is phase 0. Phase 0 means this is the one neighborhood, one hop neighborhood, because 2 raised power 0 is 1. This is the phase 1. So here 2 raised power 1, that is 2. So that means here this particular neighborhood, that means it's basically 2 hop neighborhood in both the directions in the phase 1. Similarly, this is the phase 2. In the phase 2, 2 raised power 2 is equal to 4. So here you just see that this is 4 neighbors on the left, 4 neighbors on the right, and the probe will go the 4 different hops and the replies has to come back. Then only Pi has to be winner. If the Pi has to be the leader, then it has to be elected as a leader in phase 0, then it has to be elected in a phase 1, and it has to be elected in a phase 2. Okay. So if it is a ring of this size, then Pi will be the leader elected in this particular algorithm. This is explained over here. Now this correctness is similar to big O of n square that I have explained you. Now message complexity of this algorithm. The message complexity of this algorithm belongs to a particular phase and is initiated by a particular processor. So now we are going to count how many different messages are being used to elect a leader here in this case, and how it becomes order of n log n. Now the probe distance in a particular phase k is 2 raised power k, that you know already. So the number of messages initiated by a processor in phase k is at most 4 times 2 raised power k. Why? Because 2 into 2 raised power k probes messages and 2 into 2 raised power k replies messages. If you count, it becomes 4 times 2 raised power k different messages in a phase k, which is being initiated by a processor Pi. So we have to count how many such processors will be there in a phase k. So how many processors will be initiating in a particular phase k, that we are going to compute. Now for k is equal to 0, that is for phase 0, every processor will basically initiate. So it becomes n different processors are there. Now if the phase is not 1, is if more than 0, then every processor that is a winner in a phase k minus 1 does the winner means the largest ID in its 2k minus 1 neighborhood. So that we are going to compute. So how many maximum number of phase k minus 1 winner occurs when they are occurs. So we can see this when these particular phase k minus 1 winners are basically packed densely in this particular manner. So what is basically, so the phase k winner between two phase k minus 1 winner, let us say pi, on the left it has two k minus 1 processors. So another processor pj on its right, again it will have 2k minus 1 processors. So if this kind of packing is done all around the ring, the structure, so then we can count how many different phase k minus 1 winner will be there. So that particular count, if we see the total number of phase k n minus 1 winner will be at most n divided by 2 raised power k minus 1 plus 1. Plus 1 means including this, and 2k plus 1 this. So total number of winners in a phase k minus 1 will be this particular figure, that is explained over here using this formula. Now next thing is what happened? Just pause. Start. So how many phases are there, that we are going to now find out. Now so at each phase the number of phase winners is cut approximately in half, from n divided by 2k minus 1 plus 1 to n divided by 2k plus 1. So after approximating log n phases, only one winner is left out, that is precisely max phase is log n minus 1 plus 1. So if you want to understand this particular how many different phases will be there, so you can see that how many, so it will be if we go back, so total number of phase k minus 1 winners is at most n raised to power so total number of phase k minus 1 winners is at most n raised power 2k minus 1 plus 1. So these are total number of phase k minus 1 winners. So in the end there will be only one winner. So this will become n is equal to 2 raised power k minus 1 plus 1, when total number of winners is only 1. And if we move this one over here, it will become n minus 1 is equal to 2 raised power k minus 1. So if you take log of it, both the side, so that becomes k is equal to total number of phases will be log n minus 1 plus 1. So this particular expression, we have explained you how this particular expression came, and this will represent how many number of phases, the total number of phases in the algorithm we have computed. Now we are going to count how many messages are required in this particular algorithm, how many total number of messages are flown to decide a leader in this particular algorithm. So we can see here 4n messages will be required in the phase 0, then when the leader is decided, then it will send a termination message, that will be n different messages. In all other cases So it will be the summation like this. So 4 into 2 raised power k different messages will be there. That will be a probe and reply message, and it is bidirectional. So basically 4 times 2 raised power k, that we have seen in the previous formula also. And these are basically the number of phase 2k minus 1 winners, and total number of phases will be the summation 1 to log n minus 1 that we have seen. So if we count total number of messages, so that is what I have explained. Total number of messages, it comes out to be, this figure is 5n, and this can be approximated as 8n log n plus 2, which will be of the order n log n. Now the order n log n algorithm is more complicated, we have seen, than order n square algorithm. Why? Because but it uses a fewer messages in the worst case. So it works both in the synchronous and asynchronous case. So can we reduce the number of messages even further than n log n? So we can see here that it is not possible. Why? Because there is a lower bound which is proved as n log n in this particular model, which is called asynchronous model. So in asynchronous model, this algorithm is optimal because n log n is the lower bound which is proved here in asynchronous model. So it is the theorem says that any leader election algorithm for asynchronous rings whose size is not known a priori has the lower bound omega, big omega, n log n message complexity, holds also for the unidirectional rings. So both LCR means big O of n square algorithm, and HS means big O of n log n are compared or comparison based algorithm, that they use identifiers only for the comparisons. In synchronous networks, big O of n message complexity can be achieved if general arithmetic operations are permitted and if the time complexity is unbounded. So to summarize of the leader election in the message passing system, which is the ring with the non-anonymous ring having the distinct IDs assigned, we can see the complete scenario as an overview like this, that there exists algorithm when the nodes have unique IDs, that we have seen after seeing the impossibility results. Then we have evaluated them according to their message complexities, that is, if it is asynchronous ring, that will take n log n messages. If it is synchronous ring, then it will take order n theta n messages under certain conditions, otherwise it will be theta n log n messages. All bounds are asymptotically tight. So the conclusion. So this particular lecture provided in-depth study of the leader election problem in the message passing system for a ring topology. We have presented different algorithms for leader election problem by taking the different cases like anonymous, non-anonymous rings, uniform and non-uniform ring, synchronous and asynchronous ring. So in the upcoming lectures, we will discuss about causality and the time concept in the distributed system. Why? Because we have already seen that distributed system is not having a common global clock, yet how the events are to be ordered. For that, we are going to see in the next lecture more details about it. Thank you.